Welcome to the proof of the mean value theorem. So just a reminder, the mean value theorem states that if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists some C in the open interval AB such that f prime of C is equal to f of B minus f of A all over B minus A. So for our proof, let's go ahead and just state our base assumptions. So we're going to assume or suppose that f is continuous on the closed interval AB and differentiable on the open interval AB. And now what we're going to do is we're essentially going to force this situation into a Rolle's theorem situation. And once we have done that, we're done because we already proved Rolle's theorem. So what we are now going to do is we are going to set g of x to be equal to f of x minus f of b minus f of a all over b minus a times x. So essentially we've taken the line that goes through the origin that has slope equal to the average rate of change or our desired slope, and we're just subtracting that off from that. So I claim that g of A equals g of B, or equivalently, that g of B minus g of A is equal to 0. So that's what we would need for Rolle's theorem to apply on G. So let's just go ahead and check that. So g of B, I'm going to do this in another color quickly. So g of B minus g of A is the same thing. G of B is f of B minus f of B minus f of A all over B minus A times B. And then we are going to subtract off g of A is f of A minus f of B minus f of A all over B minus A times A. And this becomes f of B minus B times f of B minus f of A over B minus A minus f of A plus A times f of B minus f of A all over B minus A. We can then combine terms. So this fraction In this fraction, we're looking at the same denominator. So this is the same as f of b minus f of a. And then we have plus I'm going to rearrange these quickly. So we have plus a negative b times f of b minus f of a. Plus a times f of b minus f of a, all over b minus a. We can go ahead and factor out this common f of b minus f of a. So if we factor that out, we have f of b minus f of a. And then we have plus and f of b minus f of a times negative b plus a over b minus a. Negative b plus a is just negative b minus a in parentheses. So that last fraction is just negative 1. So we are looking at f of b minus f of a plus negative 1 times f of b minus f of a. And this is just 0. So again, here we have that, therefore, g of b minus g of a equals 0. And therefore, g of a equals g of b. So at this point, we have that g has the endpoints matched. Right? So g of x, or g of a, equals g of b. G is continuous on AB, since subtracting continuous functions still results in in a continuous function. Right? So the difference, since the difference between continuous functions is continuous. And similarly, G is differentiable on the open interval AB, since the difference between differentiable functions is differentiable. So what we get then is, by Rolle's theorem, which we have already proven, there exists a C in the open interval AB such that G prime of C is equal to 0. And so we know that G prime of C is equal to F prime of C. Well, before we get there, recall that G of X was equal to F of X minus F of B minus F of A all over B minus A times X. So G prime of X is F prime of X minus F of B minus F of A all over B minus A. That was all just a scalar in front of X, or a coefficient in front of X. And so, or then we have that G prime of C equals F prime of C minus F of B minus F of A all over B minus A. And this must equal 0 since G prime of C equals 0. And therefore, F prime of C is equal to F of B minus F of A all over B minus A. So that is our proof of the mean value theorem, taking advantage of that special case Rolle's theorem, which we already proved.